and welcome to Atmospheric Physics 1. I'm your instructor, Grant Petty. This is one of a series of short videos that I'm making to supplement the lectures and other course materials. More will be placed in the AOS 330 playlist on my YouTube channel. Homework assignments requiring you to solve problems are an essential part of almost any physical science course. The purpose of problem sets includes reinforcing the relationship between textbook concepts and real-world applications, and helping develop a broad set of analytical skills that will serve you well in almost any technical field you might go into after you graduate. In the shorter term, developing good problem-solving skills will improve your ability to successfully complete assigned homework and make it more likely that you'll earn appropriate credit for even partial solutions. It's easy to overlook the range of distinct learned skills that must be brought to bear in the solution of almost any problem. If you're still weak in any one or more of these skills, then the whole process will become an ordeal, an exercise in frustration, rather than learning. The solution of any homework or exam problem, regardless of the details of the problem, invariably entails the following steps, the first of which has ideally been completed before you even see the problem. Knowledge, learning the relevant facts and theory. Analysis, applying familiar facts to an unfamiliar problem. Execution, the mechanics of working in a solution. Validation, convincing yourself that your answer is correct. Understanding, drawing the appropriate lessons from the exercise. If you struggle with any of the first three, then your success in obtaining a solution at all may be in doubt. If you skip the fourth step, then you can never be completely confident that you did the exercise correctly until you get your grade back. If you don't take time to understand what the problem is telling you, then the effort will be at least partly wasted, even if your solution is correct. Let's review each of these steps in turn. Let's start with step 1, which is acquiring the relevant knowledge. The purpose of your instructor's lectures and your textbook is to impart knowledge of the subject matter of your course. Knowledge includes observed facts, for example, the composition of the atmosphere, and governing principles, which include things like conservation of energy, the ideal gas law, and other physical laws. It's not enough to just memorize facts. You must take time to understand how they are interconnected and work together. Your goal should be to learn how things work. A random pile of facts might look like this. An organized body of interconnected knowledge, on the other hand, might look more like this. A key question that a lot of students still actually struggle with is how to study. To start with, you need to pay attention to the context in which facts are presented. Why is the instructor making a particular point? Is it knowledge for knowledge's sake, or is it an important brick in a larger wall? What process or situation does a particular equation describe? Knowing an equation by heart is of no value if you don't know what it's good for. What assumptions were used to obtain a particular solution? Even if that equation seems to describe something you need, such as the relationship between, say, pressure and altitude, it's worse than useless if its underlying assumptions are invalid for your particular problem. Actively answering all of the above questions in your own mind is an essential part of studying. If you passively read your textbook as if it were a mere recitation of disconnected facts, you will not be prepared to correctly apply your knowledge. The same warning applies if you read a homework problem first, and then dive into your textbook on a scavenger hunt for the one key factor formula needed to solve it. So we just talked about acquiring knowledge. Let's turn to analysis. Your goal is to choose a relevant set of facts and relationships from your body of knowledge and to string these together in an unbroken chain of logic leading from the givens of the problem to the desired solution. If any link is missing, then the chain is incomplete and therefore worthless. You will need to take stock and see if there's another piece of information that you overlooked. Sometimes that missing information is not a textbook formula or a fact, but rather a reasonable assumption, also known as common sense. You need to plan your solution. What information are you given? What are you being asked to determine or calculate? Which additional facts or reasonable assumptions are likely to be relevant? Which governing principles or relationships apply? Most important, how do the facts, assumptions, and relationships at your disposal allow you to logically get from your given information to your desired solution? Reminder, every step must be logically and factually correct. Every step should take you closer to your desired solution. Avoid blind leaps of faith, which means basically missing links in the chain. If there's a missing link, then the chain doesn't hold. Try to keep an eye on the big picture. There's more than one way to get from Chicago to St. Louis. But you probably don't want the one that goes through Denver. So we talked about analysis. Let's talk about execution. That's the mechanics of working out your solution. Once you've mapped out your solution strategy, you need to assign suitable symbols to represent each relevant quantity. You should specify values, including units, for those quantities. And you need to convert to a common set of units. And I strongly recommend using SI units, meters, kilograms, seconds, and Kelvin. You need to manipulate the symbols algebraically to obtain what I call a symbolic solution. You should verify the dimensional consistency of your solution. Finally, you need to compute any required numerical solution based on the previously specified parameter values. All of the above steps are straightforward and can become second nature to any sufficiently motivated student. Fluency is acquired not so much by study, but rather by practice. Most of you, in fact, already know the relevant operations. It's sheer repetition that will make them automatic. Let's say that the problem is to calculate the area of the following rectangle. It's got a width of 18 inches and it's got a height of 25 centimeters. Very trivial. The first step is to assign symbols. And so we'll call the width W, we'll call the height H, and the area that we're looking for, we'll give it the label A. That's the desired unknown. The next step is to specify the values of the parameters. In this case, we had 18 inches for the width, 25 centimeters for the height. And we want to convert to a common set of units. And I strongly recommend, in fact, in my course I require that we use SI units for intermediate calculations. In that case, the width becomes 0.457 meters, and the height becomes 0.25 meters. So the symbolic solution, in this case, is very straightforward. You don't even need to derive anything. We simply need to remember that the area of a rectangle is the width times the height. So our symbolic solution, in this case, is simply that A equals WH. And that is one of the most important parts of your solution, is a symbolic solution. I'll come back to that shortly. Now, the next step is to verify dimensional consistency. We have a length W times a length H, and so the product of those two is a length squared. And we expect an area to be expressed in units of length squared. So we have length squared on the left, and we have length times length on the right, and that is dimensionally consistent. And we've convinced ourselves that this is a dimensionally consistent expression for the variable that we're trying to get. The final step is to compute the numerical solution. We already have our width and height in a common set of units, meters, part of the SI system. So we know that if we plug in the values in meters on the right-hand side, we're going to get meters squared out of the left-hand side. So we just have to put in 0.457 times 0.25, do the calculation on our calculator, and get 0.114. And we know that that's in meters squared. And so that's our numerical solution. And between a symbolic solution above and a numerical solution below, we're done with that problem. Now, just to come back to the subject of symbolic solutions, that's the part that matters most. As a rule of thumb, I give at least 2/3 credit for a correct symbolic solution. A correct numerical solution can't earn more than about 1/3 credit if the symbolic solution can't be found or is incorrect. I really want you to emphasize finding the symbolic solution first, and then the numerical solution follows very quickly and easily from that. Why the emphasis on symbolic solutions? First, there's the generality of the symbolic solution. If a parameter value changes, only steps 2 and 5 need to be repeated. We just have to do step 2, which is to specify the values and convert to common units. And then step 5, plug those changed values into our calculator and get the new numerical solution. The second reason for emphasizing symbolic solutions is clarity. It's easy to see the role each variable plays in the solution and which variables play no role at all. It's easy to quickly verify dimensional consistency and thereby rule out an obvious error in your solution. If it's not dimensionally consistent, it's not correct, period. Finally, and maybe this is most important in the short term, it's easy for your grader to tell at a glance whether your solution is basically correct, even if you made a numerical or unit conversion error. If the grader sees that the symbolic solution is correct, you're going to get the bulk of the credit, even if you goofed up in your calculator or did something funny with the unit conversions. And finally, working with symbolic solutions improves your analysis skills. You learn to think about how things work in terms of general relationships, rather than in terms of numbers specific to just one particular case. The textbook that we're using goes into greater depth on the following topics. What a bad, but all too common, solution write-up looks like and why it's bad. That's in section B2. The essential features of a good solution write-up, including symbolic solutions, dimensional consistency, mathematical consistency, numerical precision, and we have a summary and an example of a good write-up in section B3.5 and B3.6. Maybe most importantly, a comprehensive checklist for your homework solutions, and I'd like you to use this. We'll be using that checklist when we evaluate homework solutions that are turned in. We just talked about the execution of your solution. Now let's talk about validation. And that's convincing yourself that your answer is correct. You have arrived at an answer and duly recorded it on your homework sheet. The dimensions work out. The problem asks for a radius, for example, and sure enough, your answer has units of length. That's great. At this point, many students consider their work done, put their pencil down, turn in their answer sheet, and just maybe cross their fingers. But it's not necessary to leave everything to chance. You can reduce your chance of turning in nonsense and possibly getting 0 credit for your hard work by taking a few extra minutes to think about whether your answer makes sense. Here are some examples. If your solution consists of a mathematical relationship, what variables appear in it? Are they the variables you expect based on your understanding of the problem? Is the relationship what you would expect it to be? When you substitute reasonable values for the variables in a relationship, can the result be positive, negative, or 0? Is the sign you get what you expect it to be? What magnitude or range of magnitudes do you expect your quantity to take on in typical situations? Is the magnitude of your result consistent with the expected range? If the quantity is a vector, is the direction reasonable? Is there a special case or limit for which you know what the answer should be, either exactly or approximately, and does your solution yield that answer? If you run into anything during these steps that says there's something maybe a little wrong here because there's something wrong with the values that come out or the magnitude just doesn't seem right, then maybe it's good to go back and check and make sure whether you still think that your solution is actually correct. We just talked about validation. Now let's talk about understanding. That is drawing the appropriate lessons from the exercise you just solved. Many assigned problems aren't intended merely to test your knowledge or exercise a particular skill, but also to drive home a specific point. It follows that if you simply write up your problem solution, convince yourself that it appears to be mathematically and numerically correct, and then walk away from it, you are shortchanging your own meteorological education. Your insight into the subject matter will mature more rapidly if you routinely set aside a little extra time to reflect on the following questions. What general principle does the problem demonstrate? To which parameters of the problem is the outcome most sensitive? Examine this question not only in mathematical terms, but also keeping in mind the likely range of parameter values encountered in a real atmosphere. For example, both the acceleration due to gravity and the temperature might appear in a particular relationship. While both vary, the temperature at the Earth's surface is likely to vary by a far greater amount than g, that is, the acceleration due to gravity, and therefore to have a dominant influence on variations in your result. Are there values for the parameters of your problem for which your solution breaks, either mathematically, for example, division by 0, or by violation of a key assumption, for example, that some parameter x is very small compared with 1? Could those parameter values actually occur in the Earth's atmosphere or on another planet? In addition to the specific scenario of the assigned problem, can you imagine other real-world scenarios to which the same general principles might apply? An example might be how pressure in the ocean changes versus how pressure changes in the atmosphere. To summarize, we just walked through what I call the 5 steps to success in solving physical problems: knowledge, analysis, execution, validation, and understanding. That concludes this module on physical problem solving.